Quantum mechanics has revealed to us some very bizarre and counterintuitive properties about the universe. Quantum computing takes advantage of these properties to build computers that seem quite magical. The purpose of this talk is to impart some intuitive understanding of how it is that quantum computers work. To understand quantum computing, we're going to do a little bit of math, some computer science, and physics. We start with the notion of a bit, which can be in a 0 or a 1 state, usually represented by high or low voltage on a wire. We can represent that bit in a mathematical notation called a c-bit, which is a vector with 2 values, as you see here. And the top value tells us whether the c-bit represents a 0, and the bottom value tells us whether it represents a 1. And so this first c-bit on top is a 0 bit, and the one on the bottom is a 1 bit. There are 4 operations you can do on a single bit. Identity, which leaves it the same, negation, which flips it, constant 0 sets it to 0, constant 1 sets it to 1. And there are lots of different ways to represent a function. We can think of them as gates on a circuit board, or we can, and you see here, gates for identity negation, or we could think of them as mathematical functions that take an input like x and return a value. In the case here, constant 0 returns it to 0, constant 1 makes it a 1. We can also represent functions as truth tables or maps that show you how each input is going to be transformed into an output. And you can see those maps here. For example, constant 1 takes 0 and 1 and maps them both to 1. The other way to represent a function is using a matrix. For every function, there is a matrix that can be applied to the c-bit in such a way that that c-bit will be transformed into a new c-bit. So here, for example, the identity matrix 1001, when you multiply it by this c-bit, if you remember how to do matrix multiplication from school, that's great, it turns it into a c-bit, in this case the same one. So the identity matrix will turn a 0 into a 0 or a 1 into a 1. And the negation matrix 0, 1, 1, 0 will turn a 0 into a 1 and a 1 into a 0. And you can see how constant 0 and constant 1 also have matrices that operate their functions onto c-bits. While some esoteric functions cannot be executed by computers, pretty much all the ones that we know can be implemented on computers and also represented as matrix transformations. In this particular example, we see a matrix representing a gate called a C0 gate, which takes 2 bits in as input. And you don't see the 2-value c-bit here, you see a 4-value c-bit. A 4-value c-bit corresponds to a 2-bit number, which can be 00, 01, 10, or 11, 4 different values. And this c-bit, which has a 1 in the 3rd position, is equivalent to a 10 number, or 2. And in this case, C0 is transforming that 10 into a 11, transforming the 2 into a 3. Just because a function could be computed, though, doesn't mean it can be computed quickly. And one thing that computer scientists try to do is to understand the order of complexity of an algorithm. And that means if you increase the input size by 1 more bit, how much longer does it take the program to run? Maybe it doesn't take longer at all, in which case it's a constant order of complexity like order 1. Or maybe it rises linearly like order n. Or maybe it's a video processing algorithm for a screen that's n pixels across, and that would take n squared complexity. But then there are other algorithms that increase exponentially. So as you add 1 more bit, it might take 2 or 3 times as long to run the program. And you can see how quickly these functions rise. These are the kinds of problems where if you try to run them on large input sizes, it may take months or years or centuries or millennia for conventional computers to actually produce an answer. The canonical exponentially hard problem is called traveling salesman problem, which seems deceptively simple. Let's say that you're a salesperson who needs to visit 7 cities. And what you want to know is, what order should I visit these 7 cities in order to have the shortest route? To solve this problem, the computer must by brute force look at every possible route that the salesman can travel, remembering along the way the shortest one that it's seen so far. The problem is that if you have 7 cities and you want to add an 8th, that creates 8 times as many routes for the computer to look at. If you add a ninth city, 9 times as many routes. So this is an algorithm that scales up at the rate of n factorial. So the brute force solution has an order of n factorial. Mathematicians have figured out some clever tricks and are able to come up with better algorithms that have an order of 2 to the n that are exponential. But they can't do better than exponential. That is, unless, of course, you decide not to travel and just sell your wares on eBay. And that would be a constant order of complexity. So if you have a computer today that can solve the traveling salesman problem for, say, 50 cities, and it took a certain amount of time for the computer to do that, and you say, what happens if I want to add cities? How much faster do I need my computer to be to solve the same problem with 51 cities or 52? What if I wanted to add 100 cities? Well, it turns out that even with Moore's law, computers get twice as fast every 18 months. So in order to get twice as fast 100 times, it would take 150 years of progress by Moore's law for the computer to be able to solve that traveling salesman problem, to be able to go from doing it from 50 cities to 150 cities. Every time you add 100 cities to the input, you'd have to wait 150 years for the computers to be powerful enough to do it. That's what makes the traveling salesman an exponentially hard problem, or an NP problem. So now we can look at all the computable functions, and we can split them up into the easy linear ones, the harder polynomial ones, and the really hard exponential ones, like traveling salesman. As you're trying to think about whether to tackle exponentially hard problems, it's helpful to distinguish the ones that are NP from the ones that are NP hard. NP hard problems, like traveling salesman, are not only hard to solve, but if somebody said, here's the solution, and you wanted to verify it, it would take an exponentially long time just to verify the solution. If I said, here's the fastest route for 50 cities, you'd still have to check it against every other possible route. An NP problem is very difficult to solve, but if I gave you the answer, you could very quickly verify it, such as factoring a very large number. If I gave you the factors, you could multiply them to verify that, in fact, the solution is correct. So, trying to solve exponentially hard problems takes a massive amount of computation, and that's why people invest in supercomputers like the ones you see here. These computers are running massive numbers of parallel cores, in some cases even more than 10 million cores simultaneously. And there's so much compute power that it costs over $10 million a year in electricity bills just to power every one of these computers. But the capabilities of these supercomputers are quickly flattening out, because as we build them with more and more parts, the parts themselves are subject to failure, and it becomes more and more difficult to actually complete any operation. Furthermore, even if the processors are following Moore's law, the memory performance is not. And we also know that Moore's law is not infinitely sustainable. In fact, most people suspect that we cannot create smaller geometries than 5 nanometers, and so we are reaching the limits of Moore's law today. We're now going to switch gears and start talking about physics, specifically the double slit experiment. In this experiment, we project particles through 2 slits in a wall, and then we measure where they hit on the other side. And as you'd suspect, if you send particles through 2 holes, they will cluster on the other side near where their holes are. Well, that's certainly true for discrete particles, but what if we were to push water through those slits in the wall? When they come out the other side, the water will be moving in waves that then interfere with each other. And when those waves hit each other, they're going to create higher peaks and valleys, and you'll have this interference pattern. When it gets to the other side, that interference pattern will have more and less water hitting the other side in this oscillating pattern. So if you measure how much water hits the wall, you'll get these bands rather than two discrete measurements like you had with particles. In 1805, Thomas Young performed the first double-slit experiment to determine whether light is a particle or a wave. Would it produce the clustering that we see on top, or would it produce the bands like water would do on the bottom? And he discovered that, in fact, light is a wave, and it creates the bands. And you could do this at home with cardboard and slits. Just shine a flashlight at the cardboard, and you'll see that you'll get these bands on the other side. Later, Einstein proved that light is actually a particle. So that seemed to create a mystery. Why does light act like a wave in the double slit when Einstein proved that light is made up of discrete photons? In 1927, the double slit experiment showed that electrons also behave like waves when you push them through the wall. That's really strange. It's not only light that behaves like a particle and a wave, but electrons also behave like a wave, even though we know them to be discrete. In 1928, the same wave behavior was duplicated with just a single photon. This is the spookiest result of all. What this means is that Germer would push a single photon through the wall, not knowing which hole it went through, and then do that again and again and again, and then collect the historical results of all the places where the photon hit the wall on the other side. Now, because the photon was going through one at a time, you would think that it goes through one hole or the other, and that over time you'd get a collection at one hole or the other, like you would with particles. But strangely, when these photons would go through, even one at a time, they behaved as though they were in a wave, like they were interfering with some other photon and hitting the other side in only where these bands are. In 1970, Richard Feynman predicted that if the double slit experiment were repeated with these single photons in a way where we actually watched the photons and we measured which holes they went through when each one went through, then it would stop behaving like a wave and it would behave like a particle because we were watching it. And in fact, in 1974, this was confirmed. And they did it again using electrons. And when either photons or electrons are sent one at a time through the double slits, they behaved like a wave unless they were being watched and measured, in which case they behaved nicely, like the particles they're supposed to be. In 2013, this was done again with not just light or electrons, but very, very large molecules. And again, even these large molecules, when they went by themselves without being measured, they produced this very, very strange result, which means that this isn't a property of light. This is how everything in the universe behaves. When we're not measuring it or watching it, it exists as a wave. It doesn't exist in just one place, but rather it exists in any possible place with different probabilities. This is how Schrodinger's cat could be both alive and dead at the same time until you open the box to look at it. This phenomenon of existing simultaneously in different states is extremely counterintuitive, but it's fundamental to quantum mechanics. The double slit experiment demonstrates to us that nothing in this universe actually exists in one fixed location until such time as it interacts with other particles, such as when it's measured. Until then, everything exists in a superposition. It exists everywhere at once, of course with different probabilities. And particles in the superposition can actually interfere with itself as it moves into those other positions. When a particle in superposition does interact with some outside particle, the superposition collapses. That's what we call decoherence. And from that point forward, the particle will then occupy only one positional state. A conventional computer uses bits to represent an electron flowing through a circuit. In a quantum computer, we use qubits to represent particles that are isolated such that they remain in superposition. And therefore, a qubit will simultaneously be in a state of 0 and 1. We represent this mathematically the same way we represent c-bits with a two-value vector. And in fact, c-bits are just a special case of qubits where you can use only zeros and ones so that your c-bit is going to act like a 0 or a 1 bit. But in a qubit, you have two values that show you the probability distribution over 0 and 1. Qubits act like both zeros and ones, but eventually when they collapse, they will collapse according to this probability distribution. The one on the left here, 1 over root 2, 1 over root 2, when you square each of those numbers, you get the probability of the qubit resolving to either 0 or 1. In this case, because both these values square to 1/2, or say 50%, this qubit has a 50-50 chance of collapsing to a 0 or a 1 bit. The second qubit, when you square those, you get a quarter, 3/4, so it has a 75% chance of collapsing to a 1. The third one is just like a C bit that's 1, 0, because when you square it, you are going to see that this is going to become a 0 bit. The last one, when you square those, again, you get 50/50, even though there's a negative sign. Somehow this qubit is different than the first one because that is a negative sign, and yet when it collapses, it will behave the same. It is really important to understand this qubit notation, so just in case my explanation wasn't clear, I include this slide so that you can go through it step by step again yourself. Now, just like we can apply matrices to C bits, we can apply matrices to qubits as well. In this case, we apply the 0, 1, 1, 0 negation matrix to a qubit. And as you can see, if you do the matrix multiplication, it flips the values in the qubit, just like the negation matrix does to a C bit. In quantum computers, the transformation matrices that represent functions aren't restricted to just ones and zeros. Here you see a quantum function called a Hadamard gate, which is the most important quantum function to understand because it converts C bits into qubits. In this example, we show what happens when you apply it to a 0 bit or to a 1 bit. H of 0, that notation means let's apply Hadamard to a 0 bit. And as you can see, it takes this matrix 1 over root 2, 1 over root 2, 1 over root 2, negative 1 over root 2, and does matrix multiplication on a C bit representing 0. Again, just a special case of a qubit. And what you get if you do that multiplication is a qubit representing a 50-50 chance of resolving to 0 or 1. So it takes this regular bit and gives it superposition. Similarly, if you apply H to 1, you multiply the Hadamard matrix times the 0, 1 C bit, and what you get is 1 over root 2, negative 1 over root 2, which collapses 50-50, 0, 1, just like the other, but it somehow is different because it has the negative sign. We can represent Hadamard gates as machines called Pete machines. Terry Rudolph, who wrote Q is for Quantum, named these machines after his friend, a quantum computer scientist named Pete. And a Pete machine functions like a Hadamard gate. You put a white ball in representing 0, and out comes white balls and black balls, 50-50. When you put black balls in representing 1, they also come out 50-50. The Hadamard gate is its own inverse, which means when you apply Hadamard to a 50-50 qubit, it puts it back into a regular C bit. So in these examples, you can see that the Hadamard gate matrix multiplied into 1 over root 2, 1 over root 2 gives you the 0 bit. And if you multiply it times 1 over root 2, negative 1 over root 2, it turns it back into the 1 bit. So what's interesting is that if you apply Hadamard gate to a 0, you get a 50-50 superposition. And then if you apply a Hadamard gate to that, it goes back to 0. Similarly, if you apply Hadamard to a 1, it goes to a 50-50 superposition. And then apply it again, and it returns it back to its original value of 1. Think of this as two Pete machines in sequence. If you drop a white ball into two Pete machines, it'll come back out white. If you drop in a black ball, it will come out black. But don't peek at it while it's in between the two machines, because if you peek at it, that will collapse the superposition, and then out of the first Pete machine, you'll just see white and black balls. And when they go into the second Pete machine in sequence, they won't be reverted. They'll again come out as white or black balls 50-50. So it's very important to maintain superposition inside a quantum computer. Inside the quantum computer, the white ball is in a superposition state of being both white and black. And Terry Rudolph in Q is for Quantum represents this with this cloud notation. Similarly, a black ball dropped into Pete is also going to be superposed, and it's either going to be white or black, but remember that a 1, when going through a Hadamard gate, has a negative sign in the bottom value. And so we record that negative value with a negative sign in the cloud notation. We can take these superposed qubits now, and we can have them go through regular gates, like NOT gates. In this example on the left, the NOT gate flips the qubit going in. So the qubit, remember, is both white and black. Its white instantiation turns black, its black instantiation turns white. Similarly, the superposition with the negative sign, the white one turns black, and the negative black one turns negative white. Because that negative sign, if you run a negation matrix on a qubit with a negative sign, the negative sign stays there. On this slide on the bottom, you can see an illustration of a typical quantum computing circuit. And as you can see, in this case, there are 4 bits going in, all zeros. The 2 on top go through Hadamard gates, become superposed. Then you can see that those qubits do certain things. They go through a C0 gate to the bits below. And they might go through some other XZ gates. And then the ones on top go through a Hadamard gate. That brings them out of superposition, and then they're measured at the end. We talked about gates that operate on single bits, but of course there are many gates that operate on multiple input bits, like and OR. In these examples, let's look at how multi-qubit numbers might go through a gate. First, we'll look at a NOT gate. Well, NOT only takes a single qubit. So in this example, the NOT gate will take just the first qubit of the 2-qubit number and flip it, in this case, white to black or black to white. A C0 gate in conventional computers takes in 2 bits. The first bit is a control bit, and if that control bit is a 1, then the gate flips the second one, called the target bit. If the control bit is a 0, then it doesn't do anything to the second bit. In no case does the control bit ever change. So here you can see what's happening is that a superposed 2-qubit number might go into the gate, like black, black. And if it goes in black, black, it's going to come out of the C0 gate black, white, because the control bit will cause the target bit to flip. If it goes in, when it goes in as white, black simultaneously, it'll come out white, black, because the control bit is 0. So as you can see, there's a superposition of the 2-qubit value going in and another superposition of the 2-qubit value coming out. C-swap is another kind of gate. In this case, it takes a control bit, and if it's 1, then it swaps the other 2 targets. And you can see here, for example, there's a qubit with, it's a 3-qubit number, and right now it's superposed with 4 different combinations. And if we look at, say, the second one, black, black, white, when it goes in through the C-swap, because the first one is black, representing 1, the C-swap swaps the next 2 values, so you get black, white, black, and a new superposition coming out the other side of the gate. Now that we've reviewed the math, physics, and computer science of quantum computing, we're ready to construct our first quantum computer. And it's going to solve a problem borrowed from Q is for Quantum. The problem we're trying to solve is that we're part of a gang robbing a bank, and we know that the bank has 4 gold bars in it that we want to steal. But in the vault, there are also 4 fake bars that are not gold. In addition, the bank has several decoy vaults that all have 8 fake gold bars in them. The bank manager is able to keep track of which room has real gold bars and where the gold bars are by using something called an Archimedes machine, and every vault has an Archimedes machine in it. The Archimedes machine allows you to input an address of a gold bar in that vault, and it will tell you if it's really gold or not. Every vault has 8 gold bars, and so it has a 3-bit address, ranging from 000 to 111 or 0 to 7. And you can take 3 balls, white or black, corresponding to that 3-bit address of a particular bar. You can drop those 3 balls into the Archimedes machine along with the black ball and the target input. And if there's a gold bar at that address, the Archimedes machine will turn the black ball into a white ball. And that's how you know that's a real gold bar there. If it's not a real gold bar, then the black ball will just pass through without change. Now, we only have room for 8 bars in our getaway van, so we don't need to know which gold bars are real when we find the vault, but we need to know which vault is real. When we walk into one of these vaults and start running the Archimedes machine, we might get lucky and the first bar we test happens to be gold, but if it's not, we don't know whether that happens to be a fake bar or whether all the bars in that room are fake. And with 8 bars, we're going to have to run the Archimedes machine 5 times before we know that this is not a real vault. That's a big problem for us because the police are coming in 8 minutes and the Archimedes machine takes 5 minutes to run. So we're only going to be able to run the Archimedes machine once. You might be interested to notice that if we had 16 bars, we would use a 4-bit address, or 32 bars, a 5-bit address. And if we had 16 bars, we'd have to run this 9 times. 32 bars, we'd have to run it 17 times. About twice as many times as we increase the number of inputs of the Archimedes machine. So this is an example of an exponentially scaling algorithm. We only have time to run the machine once, and so we're going to have to convert this computer into a quantum computer. That's why we brought with us PEAT machines. We can attach a PEAT module to every input of the Archimedes machine and to every output. What's going to happen when we do that? Well, let's take the easy case where we find ourselves in a decoy vault. In a decoy vault, the Archimedes machines don't flip any targets regardless of the address. Although you can't look inside each Archimedes machine, in the fake vaults, the Archimedes doesn't do anything to the inputs. They just pass through, right? All the white balls go in, they'll come out white. Your target's going to go in, it's going to come out as it is. So we know that if we drop in 3 white balls as the address in a fake vault, they're going to come out white. What happens if we're in a real vault and we drop in 3 white balls? As each white ball passes through a PEAT machine, it's going to come out superimposed as both white and black. The black ball that we put in the target will come out superimposed as white and negative black. The 4 qubits that now go into the Archimedes machine can be in any combination of each of the superpositions. So you get a superset of all possibilities. And those 4 qubits can now exist in 16 different combinations that you see here. There's a vector here with 16 possibilities: white, 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 black, white, white, black, white, white, etc. And for the possibilities that include the negative black option, you see the negative sign carries through within that overall 4-qubit number. Now, let's just say we're in a room that's the real room, and the 4 gold bars are at 001, or white, white, black, 010, or white, black, white, 101, black, white, black, or 111, black, black, black. I'm just picking those 4 values as an example. As the qubits flow through Archimedes, and Archimedes is simultaneously operating on every one of those possibilities. For the possibilities that include the real gold bar addresses, Archimedes will flip the target. And so when the qubits flow through Archimedes, they'll come out transformed into a different vector of 16 possibilities that you see here. And in this vector, it's the same as the first one, except in the possibilities where the first 3 bits correspond to real addresses, the 4th bit is flipped. And you see those in red, the ones that are flipped. Now, we have 16 different possibilities. We can take that 16 set and we can factor out white, negative, black. We can factor out the qubit on the right, right? And so we don't really care what happens to that qubit on the right. So let's factor that out, and what we're left with is the 8 possibilities of what those 3 qubits are flowing through the address locations. Stick with me for just one slide. We're almost done here. Remember that we're tracking the 3 qubits on the left as they've finished Archimedes and they're getting to the peak boxes. And we know that there's 8 different simultaneous states that they're in, which we see in this vector. Now, regardless of what state it's in, when these 3 qubits go through the peak boxes are going to randomize each of those qubits. So they may get to the 3 peats as white, 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 but they're going to come out as either white, 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 black, white, black, white, white, black, 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 white, white, black, white, black, 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 white, or black, black, black. In fact, it doesn't matter which one of these states you look at, each one of those states is going to be randomized into 8 more possible states, all really variations of white, 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 black, white, etc. And the only difference is where the negative signs are. Those with negative signs are going to keep their negative signs. And what you get is this simultaneous state of 64 different combinations of qubits coming out of the peat box. Now, the reason this actually is helpful is that if you look at that first column of states, all the white, white, white ones, half of them have negative signs and half of them don't. And what that means is when you look at the probability of 3 white balls coming out, the probability of that happening is actually 0. In a real vault with real gold, there's a 0 probability of getting 3 white balls out. So when we put 3 white balls into one of these Archimedes machines in a fake vault, they all come out white. When we put it in a real vault, they're going to come out in some other state other than 3 white balls. What's happening here is very similar to what we saw in the double slit experiment. In the double slit experiment, as individual particles went through in multiple states simultaneously, and those particles interfered with themselves, we saw that interference on the wall at the end when those particles were measured. Here, we're seeing the qubits interfere with themselves, and the negative signs canceling out the positives, just like the high and low points of a wave in the double slit experiment. And although we can't see what's happening inside the Archimedes box, we can see the interference pattern happening. And because that interference pattern is happening, we know we can infer certain things about the problem we're trying to solve. Hooray, we built a quantum computer that in one step can get us the answer as to whether or not we're in a room with real gold or fake gold. And in fact, if we had 16 bars or 32 bars, we could still run this Archimedes machine just once, and with the same logic, we would know if we were in a decoy vault or not. Hopefully now you've got at least some sense of how quantum computers work, and we can talk about applications of quantum computers. You can see how quantum computers can change the order of complexity of a problem. We can now take NP hard problems, like traveling salesman, and make them NP. We can take NP problems, like factoring a large number, and make them quantum polynomial, or QP. The first type of quantum computer invented by D-Wave is a quantum annealer. This is known as an adiabatic model of quantum computing, akin to an analog conventional computer, where qubits can represent different values, not just 0 and 1. And just like in conventional computers, it's useful for certain types of algorithms, but you can't use it to execute any logical circuit. And so quantum annealers are real quantum computers, but they're not generally applicable to solve any problem. The next level of quantum computing is when we do have a circuit model computer, and we don't necessarily have enough control of it to be able to use it without error, but it does operate using quantum principles, and therefore it allows us to model the quantum behavior of particles. And these early quantum computers are very useful for simulating the behaviors of small particles that are subject to quantum mechanics. And then finally, we talk about universal quantum. This is the end goal of quantum computing, if you will. In universal quantum computing, we have circuit models that are error-free, that are scalable, and we can run any circuit on these computers. This is just an example that BCG compiled of different applications and different companies and different industries that can use quantum computing to solve problems. And we'll double-click on a couple of these. The first one that's pretty well known is the ability for a quantum computer to one day crack encryption protocols like RSA. And there's lots of speculation that the NSA, for example, has a quantum computer specifically to try to do this. I think it's inevitable that one day this will happen, but in order to crack RSA, we're going to need many, many, many qubits, many more than we're going to have for a long time. And when that day happens, there will be a forklift change of our encryption protocols, and there are protocols that are immune to quantum attack. And so I think we're going to go through a period like we did with Y2K, where people will freak out for a few years, we'll swap out our encryption protocols, and then things will go back to normal. I mentioned that early quantum computers can be used for simulation, and a very good application is modeling catalysis. It turns out that some meaningful percentage of the world's power supply is used to create ammonia for fertilizer. And we don't really understand how nitrogen-fixing bacteria do it so efficiently, but if we were able to model catalysis with quantum computers, we could probably save ourselves from the high-power processes that we use today. Modeling small particle behavior would also allow us to develop new battery materials. We would also be able to model how protein structures fold, and many other aspects of drug research. It would help us find drug targets. It would help us simulate the effect of new molecules within our bodies. And it would accelerate development in such a way that drug companies would get a lot more value out of the fixed time patents that they get for drug development today. I'm sure you noticed that the Archimedes computer was effectively acting like a huge, massively parallel computer, simultaneously operating on all different states of the qubits. So the more states that we can bring into a quantum computer, the more parallel and powerful it becomes. Well, each time we add one more input, if we can expand the number of inputs by one, so there's one more qubit flowing through, then that qubit can be 0 or 1, and it doubles the number of all possible combinations. It doubles the number of states that this computer will be in at any given time. Each additional qubit doubles the power of the quantum computer. And so if you add 10 qubits, if a computer can operate on 10 more qubits simultaneously, then you're increasing the power of that computer by about 1,000. In order to be as powerful as the most powerful supercomputers on Earth, we generally need about 60 qubits. And at that point, we'll have reached what's called quantum advantage, and our quantum computers will be able to solve problems that classical computers cannot solve. Quantum computers are getting more powerful every year. This is a very old graph, and so it was somewhat aspirational, and we have not kept up with the forecast. But the general idea is correct that we're seeing more and more qubits every year. Currently, the best one out there is probably the Google computer, which can operate on about 53 qubits, although they have a lot of errors in them, so it may be more equivalent, say, to a 20 or 30 qubit computer. Again, we need to get over 60 in order to reach quantum advantage. In addition to operating on more qubits, we also need to increase the fidelity, so decrease the error rate. And whether we're using ions as the particle or superconductors or other modalities, the companies and universities behind these research efforts have been steadily improving the fidelity rates of their quantum computers. Now, why is it so hard to do this? If we understand conceptually how it works and we understand physically how it works, why is it so difficult to actually build a quantum computer with, say, 60 or 100 or 200 qubits? Well, for one thing, we need to isolate these particles so they don't interact with other particles, and that means running most of these supercomputers at near 0 degrees Kelvin. In addition, it's very difficult to stave off decoherence, and so the amount of time we have to run an operation while our qubits are in superposition is very, very short-lived. Another issue is that we're dealing with extremely small particles where the amount of energy is so small that when the Hadamard gate converts the qubit back into a regular bit, it's very difficult to distinguish the zeros from the ones, and that's a reason why we see errors. There are different ways of building quantum computers. I won't go. To actually solve real-world problems, we're going to have to develop all the hardware and software layers of the quantum computing stack. We've been talking about the qubit arrays, the physical layer, but in addition, there are algorithms people are generating in order to correct for the errors we talked about, and there are compilers that basically are required in order to configure the circuits, to dynamically configure these quantum circuits that we talked about. There are languages and APIs that programmers can use on top of these compilers. And then there are software teams, application developers, who can then use these APIs to embed quantum capabilities into their programs. I and many others believe that the most successful first quantum computers will be full stack approaches. Although eventually these stacks may be decoupled, just like we've seen in most domains of technology, it's so difficult to get a quantum computer to work that it seems that the full stack approaches are moving ahead much faster than the ecosystem approach towards building a quantum computer. This is an important term, noisy intermediate scale quantum. And this refers to the state of quantum computing that we expect to prevail starting in about 2 years and probably for the next 10 years. And during this period, we're going to have quantum computers that have an increasing number of qubits with high error rate. And that means there are some problems we can solve and other ones we can't, and it's going to depend a lot upon the error correction protocols. There are many governments, universities, and companies working on quantum computing today. You can see here the 9 systems companies who I think are most active in the space. In addition, there are 3 private companies who are focused solely on building quantum computers. Rigetti using superconductors, PsiQuantum using photons, and IonQ using ion traps. My firm Bessemer is the largest shareholder of Rigetti. We're very excited about the approach they're taking, which is a hybrid approach between quantum and classical computing. Thank you for listening, and also special thanks to Andrew Helmer at Microsoft and to Terry Rudolph, author of Cues for Quantum, for much of the content of this talk.